Hi everyone. We have already established that reflecting telescopes are the way to go. They are really the standard now versus refracting telescopes. So the last big refracting telescope that was in place was back in 1905. And since then it's been reflecting telescopes for optical and IR and radio all the way. And we'll look into that a little bit more now. My two favorite optical telescopes are in Hawaii, and they are the two Keck telescopes that are sitting on top of an extinct volcano, Mauna Kea, in Hawaii on the Big Island, along with seven other optical telescopes and IR telescopes too. They all sit on the top of this extinct volcanic rim, and they are above the clouds, and they are with the snow in Hawaii. I just think it's the coolest place on earth, so I would love to go there someday. And so they are my favorite reflecting telescopes, and to look into them a little bit more, they use a secondary mirror for their reflecting. So here's a cross section. The incoming light comes in and bounces off of their mirrors. Each mirror is 10 meters, so they each have a 10-meter mirror in here, about 30 feet across, and that reflects up to the secondary mirror that is up here. So this secondary mirror is associated with a focal point that is below the mirror. So in other words, this secondary mirror does create a blind spot. You can't see past it. That is one of the problems with reflecting scopes with secondary mirrors. They do produce a blind spot, but they reflect down to what's called a Cassegrain focus after a French optician who developed it. When you have a focal length, remember focal length is the distance between the primary mirror down here and the focal point where the image comes into focus. This is the focal point at the Cassegrain focus, and that in the Keck telescopes is about 57 feet from primary up to secondary back down to Cassegrain. So about 2 to 3 stories between the primary mirror and the secondary mirror. Really amazing stuff. There is also another way to work on this through a tertiary mirror, so that this secondary mirror not only goes down through to the Cassegrain focus, but also can stop at a tertiary mirror and send that outward to what's called a Nasmyth focus. This becomes important to us later because this is where a lot of the work is done underneath the base of both telescopes. So you have two different kinds of focal points here. One focal point is at the Cassegrain focus underneath the mirror, and one focal point is at the tertiary mirror. Very, very cool. And I wanted to point out to you that my favorite radio telescope is the American Telescope in Puerto Rico, and it's a 300-meter dish that is one of the longest parabolas in the world at 300 meters. That is so much bigger than the Keck optical telescope because the visible wavelengths are much, much, much shorter and much tighter than the very long radio wavelengths, which can go for hundreds of meters. So it is worthwhile to have a dish that is 300 meters across in Puerto Rico. Their focal point for the reflecting radio waves is right up here. So their focal point is broader for these waves, and there's really less definition to these waves, as we'll look into. This is a favorite of mine because it's such a resilient system, and if anybody wants to do a project on how they did during Hurricane Maria, I would love more information about that. So I would love to know how the astronomical community did in Puerto Rico after Maria. They really have my admiration. When we look at these reflecting telescopes, we think of three powers to them, and we talk about the three powers, and we talk about them in order. The first power is its light gathering power, and the second is its resolving power, and the third and last, which might be counterintuitive, is its magnifying power. Two of these powers are related to diameter. We're going to go into that quite a bit. One of the parameters that power of a telescope is related to focal length. We'll describe that as well. So when it comes to light gathering power, let's go into that first. That's the ability of a telescope to collect light. And we are using these reflective telescopes from anywhere from infrared IR waves to radio waves. So let's explore it a little bit more. This light gathering power that is proportional to the diameter of the parabola of the mirror is based on the fact that telescopes are essentially light buckets. And it's a really good analogy to keep in your head, that the bigger your bucket is, the more rain you're going to collect, and the bigger your telescope bucket, your telescope parabola is going to be, the more photons you are going to collect. Really important thing to remember. And it's our primary way of knowing the quality of telescopes is by its light gathering power, because by gathering as much light as you can, you are able to see the faintest parts of the galaxy. So we can measure this light gathering power because it is proportional to the brightness of the objects coming in. When Galileo redesigned his refractory telescope, he was able to see very faint stars that no one knew were there. So he was able to literally gather hundreds of stars that no one knew about because he was able to gather more light into his bucket than the light that is in the bucket that is in your eyes. So you have a light gathering bucket, which is your iris in your eyes, and that's about 1 centimeter. He was able to make his telescope a few centimeters and see so much more. So that light gathering power is proportional to the brightness of what can come into it. That is proportional to the collecting area of the mirror or of the parabola. Reflective parabola is a mirror. And that is proportional to the area of the mirror, and that area of a circle that is also a parabola could be pi r squared. So that means that the light gathering power is proportional to the radius squared of the mirror. And not only that, but that light gathering power is also proportional to exposure time at that area of the sky. So let's look into that a little bit more. When we look at telescope A, that's right here, that telescope had a 1 meter radius. In other words, it was a 2 meter mirror. And when we take that 1 meter radius and square it, we get 1, which is a way to compare other light gathering telescopes to ours. Ours has a light gathering power of 1. There are no units here. And we can compare it to telescope B, which has a 2 meter radius, which means it has a 4 meter diameter, right? 2 plus 2, because radius is half of a diameter. But when it comes to brightness, we square that radius. So that radius squared, 2 times 2, means that this has 4 times the light gathering power for a mirror that is double the size. But it has 4 times the light gathering power. It means that you can either take in 4 times the brightness, or you can look for things that are much less bright, or you can take in that amount of light 4 times faster. Either way, the mirror diameter being bigger means that you can take in light faster and you can take in much fainter light. And I wanted to point out one other thing to you. If we talked about the Keck telescope, versus the 1 meter telescope. Think about it. We had the 1 meter radius and we have a light gathering power of 1. Let's compare it to the Keck telescope. The Keck telescope has a diameter of 10 meters, which means it has a radius of 5 meters, which means that 5 times 5 squared is 25. You've got a Keck telescope that can take in 25 times more light than a 1 meter telescope. And that makes the Keck telescope so important to astronomy, and especially because there's 2 of them, so that then we can actually say we can put the 2 of them together, and we will get to that in a bit. But remember that the light gathering power is proportional to the radius squared. This slide I have to redo for you, okay? Because the world's largest optical telescope is the telescope in Chile, but it is currently at 34 meters. Soon to be, there will be in 2025 from the European Union, there will be an ELT telescope in Chile. It'll be extremely large telescope, ELT, and that will be at 39 meters. So I need to correct this slide for you, but one thing you need to take home out of this is the bigger the better in terms of light gathering power and in terms of the quality of the telescope. And as we said, the radio telescopes are bigger. The world's largest is in China. It is not in Puerto Rico, but I don't like it as much. The one in China is 500 meters. And again, I put that there. Why is it so large? It is so large because radio waves are so much longer than visible wavelengths. This is going to be the ELT, the extremely large telescope in Chile. And it's just huge. Look at the cars. They're so small. So that's coming up in 2025. It is situated on a desert plateau in Chile, far above the clouds. So we will talk about why it is situated there and why Chile is a real hotspot for optical telescopes. See you on the other one.